Okay, it started. Let's go ahead.
It's my great pleasure to introduce Professor Tyrrell Rockafellar to you. Tyrrell is the founder of the convex analysis. Almost 60 years ago, he set up the foundation for convex analysis in his 1963 PhD dissertation from Harvard University. From then on, he continued to develop more and more theories for variation analysis and optimization. His research is so influential that he has won almost all prestigious prizes in our field. His book, Convex Analysis and Variation Analysis, with Professor Roger Wetz, have become the Bible for all of us working in optimization. After he retired in 2003, he became a professor emeritus of University of Washington. He worked in research even more tirelessly. He traveled all over the world to give lectures. Before the pandemic, during 2018 and 2019, I noticed he has given 20 lectures all over the world each year. He told me that during the pandemic, he cannot travel, but he has time to do research and has many more interesting results. So I'm looking forward to listen to it. Terry is the supervisor of my postdoc supervisor, Francis Clark. So I consider him as my academic grandfather. For the last almost 30 years, I usually travel to Seattle to attend West Coast optimization meeting, and Terry always organized a party in his house, and he had helped me and my research group a lot. So I'm really appreciate listen to Terry's talk again. Although we cannot see in person, at least we can see each other from the Zoom. So I'm looking forward to your talk, Terry. Terry, you can start.
All right, thank you, Jane. Let me point out here that although some of you are very high power researchers and you know a lot perhaps already about variational analysis, the aim of my talk is not to give difficult frontier ideas in the subject. I decided in these lectures to try more to make a motivational introduction for new people who don't know very much about variational analysis and to explain things from that direction. And so in some ways, this will be superficial, but what I think would be good, even for someone who has some knowledge of the subject, is to see a kind of an overview of it, where things fit together, why things are important, and why this is different. So I am looking in this lecture at a very big perspective of how this subject, variational analysis, fits into mathematics and why it's a good thing to know more about and how useful it could be. So as you see, I'm here at the University of Washington in Seattle, but I've been associated with other universities and I've traveled all over, as you heard, and have collaborated with so many people. So in some ways, the fact that we're in a computer meeting, we're all spread all over the world here is just typical of the modern scientific thing. But what I do miss is the personal contact that comes with all those visits, being together with people and all the things we say at the side, which aren't just mathematics. So let me get together to begin with here. It's good to ask what is meant by variational analysis? Where did this subject start? What does it mean? It's actually, the word variational has been known for some time, and I will get into that in a moment, but as a subject, I'm the one who gave a name to this. But what was this name and what was the purpose? So the idea was that there was a convex analysis, which I did not name, by the way. The name convex analysis was given by Albert Tucker, professor at the University of Princeton University, who was supporting my work. And he suggested that I write the book Convex Analysis and call it Convex Analysis. But then we got into extensions which go beyond convex analysis. And then there's some question, can we make a single subject that includes a lot of classical calculus and convex analysis? And so that was a project that I took on quite early. Back in the 1970s, I was already working on this. And for many, many years, I worked on trying to build this subject that was a bridge between classical analysis, convex analysis, and covered much more. And I'll explain more about that. Okay, now why was such a subject needed? Like everything in new developments, really new developments in mathematics, it was needed because traditional mathematics fell short. It had shortcomings in dealing with problems. Now, how could this be? I know that a lot of people think that a problem is a problem. Problems have always been around, and there are ways you try to solve it, but that's not the way things work in mathematics. Problems typically arise out of some kind of need. For example, you need to have an accounting system in the ancient world to know about your economic supplies. And then you needed to know various things about astronomy. And then you needed some geometry to build pyramids and temples and things like that. And then, of course, calculus was invented for the sake of physics. So there's a history into how these things happened. And the reason why variational analysis became important was with optimization problems. And there were always some kinds of optimization problems, but they became very valuable when we had computers, because computers could actually solve them, whereas otherwise they would have been hopeless. Now, and then one of the first developments that came from this was convex analysis, because people began to realize that convexity was a very essential idea in optimization. As I often like to say, while in nonlinear, in analysis in general, people make a division between linear and nonlinear mathematics. In optimization, it's between convex and non-convex mathematics. And so that was a big development. And but I assume in these lectures that the people who are listening have some background, at least in convex analysis, know something about it. And I'm aiming to show what goes beyond that. And I'm interested in explaining it to researchers who are interested in optimization and would like to know why there is much more to learn in this area and what it's about. And so the basic themes I will try to put together to see, as you know, it's a big opportunity for me as someone who has worked in a subject for a long time to present how I look at it, how it fits together, and what's important in it. But of course, everything has a limitation, and here I must stay in finite dimensions, or everything would be too complicated. And I have to, of course, emphasize the particular themes that I know. And although this is all really inspired by and much used in numerical work, there will be nothing numerical in here. This is a very theoretical talk, but I show how the theory will grow out of needs of solving problems. So let's go right away to some history to where this fits in. So there was, of course, very ancient history. It goes back to the calculus, how you get a little maximum and minimum by looking at where a derivative is zero. So there always has been some optimization, but in a very important area of that was started maybe 120 years ago or something like that, was something called the calculus of variations. And this is where we're getting the word variation. Well, calculus of variations was not optimization in the sense we know it from in operations research and numerical optimization, and instead was a rather theoretical subject. Well, everything was theoretical back then because you didn't have calculus. You wanted to solve a problem, you needed logarithms. I've seen them in libraries, very big, thick books that just give you all the logarithms of something, for going up and down, tables and tables of logarithms. There were no computers. So, but in these problems, they weren't trying to optimize production or any of the kinds of things we know in operations research. They were concerned with something more geometrical, trajectories, curves, but let's think of it as trajectories. What trajectory would be followed by a ball in terms of certain forces or surfaces? What about the curvatures of surfaces? And they wanted to optimize these trajectories or surfaces by minimizing some objective function. But this is all infinite dimensional. So the unknown is a function describing a surface or a curve. There's an unknown function. And then you have a space of functions and you're optimizing a function. And the function, the expression that you're optimizing is usually given by an integral of some kind. And then the idea of a variation was that you would derive an optimality condition by saying that if you were to you would change some parameter in some direction, then your objective should not go down. So you try to understand by varying some parameters whether you had optimality. And the variations in this area of infinite dimensional optimization and trajectories can be quite complicated. So this is not the simple subject we know, but it led to things like variational principles in physics. For example, that a lot of things, some kind of equilibrium is characterized by the minimum of energy under certain conditions. And variational principles also exist in other areas. But this, as I say, was in function spaces before there were any computers. But then what happened was computers. So new things developed, and they started around the time of computers. Computers came into being around in 1950, more or less. There were some very primitive ones, but then it started to catch on. And this was also a time when optimization split into, it grew in two different directions, like two different trees on two different sides of a hill or something like that. So on the one hand, the most immediate descendant of the calculus of variations was optimal control theory. There's even a lot of overlap. Control theory deals with things like trajectories, how you should steer a dynamical system by controlling the parameters on which it depends, how much fuel you're giving or how you're changing some angles or various parameters in a dynamical system. And this was mostly developed in Russia by Pontryagin and his collaborators, but actually a lot of the same mathematics already existed in the United States in the calculus of variations in Chicago, but they just didn't have the same way of presenting it. Then it had to, anyway, but that all grew in that direction, and that was all infinite dimensional. But at the same time, there was this branch that started with linear programming. This is how I got into optimization. Through linear programming and duality theory of linear programming, and that had a completely different character. It was more algebraic. And as you remember, it had things like polyhedral convex sets. This is a very different sort of thing than curves and surfaces. And it was not only oriented by problems like optimal, cheapest distribution of goods or transportation, things like that. But right from the beginning, it was oriented to computations, computer programs. And that's why it got the word programming. As we know from the book written by Danzig, original idea of programming was solving a program for things like distributing goods. But now the word is taken over by computer people, but that's why it's another thing. Anyway, then there are later developments, stochastic programming, and risk management, which have much more to do with uncertainty. However, you're going to model it with probabilities. It could be in various stages. It's related to finance. And as you know, nowadays in optimization, data science is playing a very big role motivationally. And this is where uncertainty comes in. But in these lectures, I can't really say anything about uncertainty because it brings in too many other things. But that's an extremely important area that I have worked a lot in. What is it meant by risk? How do you work with it? All of that is a fascinating subject. So now we get into something with at least a picture. I want to point out what made this area of mathematics very different from the beginning. And that's because computers were able to to change our view from what some people call prescriptive mathematics to descriptive mathematics. So prescriptive mathematics descriptive mathematics is where you have mathematical models that describe how things work. For example, you show that planets move in orbits. They move in orbits, but you can't control those orbits. You're just describing the orbits. But in the modern world, with the computers, we realize that there's a kind of mathematics in which we could affect how something would work, how a system would work, how something would be distributed. And that made a big difference. So in the descriptive mathematics, you're mostly dealing with equations. Equations are almost a synonym for a mathematical model. And of course, they could be finite, linear, or nonlinear systems. They could be differential equations, integral equations. There's so many kinds of equations. And the geometry behind them was a sort of a geometry behind things like curves and surfaces, or if you could imagine something in higher dimensions, hypersurfaces, and there's this abstraction of a differentiable manifold. All of these things don't really have any boundaries to them. But in the prescriptive mathematics, you have boundaries because when you have available choices, they're upper and lower bounds. It's not unlimited. And the bounds are not just on the side that you really have to worry about all these constraints, upper and lower bounds. So that means that there are inevitably going to be inequalities. And that came into us looking at convex sets and other kinds of sets that didn't have smooth edges like a surface. Could have corners and all of that complication as indicated by a set C here, which is shown as being defined by a system of inequality constraints. So I recall the definition of convexity here. It's a very simple idea, which is not new. But you know, when I started out as a graduate student and I was working in convexity, this is back in the early 1960s, there were a lot of older books that dealt with convexity and convex functions. But what did they mean by that? Well, actually, there were two versions of convexity back then. One was the more recent one had to do with the topology of infinite dimensional spaces, like the shapes of the unit ball in a Banach space, something like that, how round it is. And there's a lot of that kind of theory. Convexity is part of the study of infinite dimensional spaces. But the other kind of convexity was very geometric. It was called convex bodies, and it had to do with curvature and width and all sorts of geometric quantities are much more classical, that we think of more as related to things we learned in elementary school, but you know, on some kind of higher level. So there they had convexity, but they didn't really, but they looked at it as some sort of nice compact thing like a torus. That's not convex, but anyway, some kind of geometric objects like that. But the key to it is just this very simple idea that if you take 2 points in the set, and join them, and then the line segment lies in the set. But this includes the whole space, or half spaces, or lines. It's a very, very general idea. And it immediately leads, as people discover, to the concept of duality, because you can look at half spaces. Half spaces are designed by linear inequalities, as I've shown here. I guess I could be moving the cursor around here, in which this A has to be non-zero, or it doesn't help us here. So this is the kind of thing that's a half space. And then there's the characterization that C is a closed convex set if and only if it can be expressed as the intersection of a collection of closed half spaces. And the interpretation of this is that the set is could be expressed in principle, represented by a system of linear inequalities, but there might have to be infinitely many linear inequalities. But finitely or infinitely closed half spaces, you take any kind of intersection, that's exactly what a closed convex set is. So you see from the very definition of this is not the way people looked at it in geometry by any means. But this is how we looked at it from optimization. The closed convex sets are exactly the things that in principle correspond to linear constraint systems, which puts us squarely in the field of optimization. And now, once you are looking at such a set, your whole view of geometry differs from the classical geometry because it's not two-sided anymore. It's a one-sided geometry because of the inequalities. The inequalities make it one-sided. So now this picture gets a little ahead of ourselves, but this is a picture from convex analysis. And it shows that at a given point in this set, I chose a corner point to be an interesting point, but it could be any point of the set C. There are two kinds of things. There are normal vectors, which are in this thing called this capital N, and there are tangent vectors, which belong to this thing capital T. And they describe the geometry at that point in a one-sided way. Because a tangent vector, if a certain vector is a tangent vector, that doesn't mean that minus that vector is also a tangent vector, which is a completely different idea from classical. You need to appreciate that already here, there has to be a huge break with classical thinking. It has to be one-sided thinking. A lot of people don't like that in classical mathematics. Everything is supposed to be symmetric between plus and minuses, but here there is a big and essential departure. Right now, then there's the convex functions. Again, when I was first getting involved in this, and of course, there were some somewhat modern things coming out already in the 1960s, but I was looking at older books, and older books, the only convex functions that people were really studying around 1960 were norms on function spaces, things like that. People weren't really interested in just a convex function on a convex set. They couldn't find any theory about that. There's all those books, Bourbaki books in French, the founding of the new kinds of analysis. They pay no attention to really to this kind of thing. And they don't relate it, they just take this definition. So the definition of convexity has to do with this linear inequalities, that's how people typically learn it. It's an extrapolation or interpolation idea. If you look between 2 points, the value will be less, but that misses the geometry of it, because to look at the geometry of it, and this is another thing which convex analysis brought in a completely new idea that did not fit in any way with classical analysis, that of the epigraph of a function. Nobody ever looked at an epigraph before convex analysis. I think epigraph was a term invented by Jean-Jacques Moreau, who was very much involved in the early days of inventing convex analysis when I was getting into it myself. And so epi kind of means above. So this is the thing above the graph, and it kind of now, if you take a convex set C and then you have a finite convex function on it, then you could look at these points that are on or above the graph of this. And the interesting part is that the definition of convexity corresponds exactly in geometry to this set being a convex set. Well, that would mean that in order to study the graph of, in order to study a convex function, you have to study an epigraph, because it's the convexity of this convex, of this set, that will give you all that interesting geometry of tangent and normal cones. And then a further idea came. So when I was first working, there was Werner Fenchel in Denmark. He was a German Jew who fled the Nazis and later ended up living in Denmark. And he had started to work on convex functions, and he had some idea, conjugate convex functions. But to him, a convex function was a pair. It was a pair consisting of a set C and a function on that set. But that's very awkward to deal with that way. And so what came instead was to use an infinity. So you take this function, now you extend it beyond that set with infinity, and then you simply have a function on the whole space, but it's extended real value. It could have an infinity valued, and then you can recover the set C as a set of points where you don't have infinity. And even the definition of convexity as an inequality up there, this still works, but you have to pay attention to what happens if you are multiplying a 0 times an infinity or something. So you need some little convention, but you can still use that. And but the thing is then that you are no longer going to study the graph of a convex function. The graph is not interesting. But the classical geometry, you study the graph because the graph is is a subject of this vector space Rn+1. But if you took the graph of a function with infinity, you would not have something in Rn+1 because infinity point is not, can't be represented in n+1, but the epigraph is there, and the epigraph can cover it. So this is something that is just very, very different. Then, of course, we get into subgradients. This is something that Jean-Jacques Moreau and both and I came upon kind of independently at the same time in around 1962 or 63. And that's just where we are looking at a point where the function is finite. And well, okay, let's recall that in classical analysis, you have a way of looking at differentiability in terms of a gradient. And one way I like to use, sometimes at least, this classical notation of an error term, a little o error term. And one way to describe differentiability and a gradient is to look at a linearization of this function, which is an approximation up to a little o error term. And so we have right here this expression of a gradient in terms of this, where you have this linear term and then you have this error term here. And that just and the satisfaction of this is equivalent to v being the gradient there, and that's the concept of differentiability. But in convex analysis, what we came up with was you could look at these inequalities without an error term. Now later, when we go beyond convex analysis, the error term will come back here. That's one of the ways we get a bridge between these subjects. But here we have this inequality without that. And then what that means is that if I look at a point, here's the epigraph of here, and to make it interesting, I have a point which is kind of a corner here. And what this inequality means is that I have a linear function which does not cross over into the epigraph. And it actually corresponds, if I think about this epigraph as a convex set, it corresponds to a supporting half space. This line is the boundary of the convex half space that touches at this point. So this is the kinds of tools of convex analysis are being used not in geometry, but for analysis. So by the way, many of you wouldn't know it, but when I first wrote my book, Convex Analysis, and this came out in 1970, a lot of people were disappointed. Some important people were disappointed. For example, they said, why don't you just write about convex sets? You don't need to write about convex functions because you're just going to do convex geometry. They thought this was what we call busy work, to do it all with a function. Why do it with a, we're just creating new terminology. It's a waste of time. And a famous person in variational and classical calculus of variations, he wrote a review about my book, Convex Analysis, saying some people in numerical optimization might be interested in it, but otherwise it wasn't a good book. So all of that is because of this. Why could people say it? It's because they have no understanding of how this is a kind of a breakthrough in the concept of analysis. That you're going to look at analysis in a one-sided way. And that's where we carry on later in convex and variational analysis. It's really an exciting opening and an idea that was hard for people to swallow at the beginning. They couldn't really appreciate it. It just seemed like some nuisance, something that was in the way. All right, and now, of course, we have getting into optimization right away. We have this rule that the global minimum of a convex function is characterized by 0 being a subgradient. Now, is that a profound result? No, because if I put 0 here, it exactly means that I have the global minimum at this point. So it's trivial. So in some way, this is just notation. But what is good about it? What's good about it is this leads you to think about calculus. So if we had the classical thing, the gradient equals 0, that's trivial also as a condition. But what makes it important is the calculus lets you calculate the gradient from various structures for the function f. So that's where this has to lead. Then you have this. Then you have to have a calculus for this. All right. And there's another interesting thing in this convex case. You can exactly come back to the differentiable case that The function is differentiable corresponds exactly to where there is a unique subgradient. But then also a little more dramatically here, you can even have subgradients where the function is going to jump to infinity. So here I have a boundary, and then here somehow these subgradients can get steeper and steeper, and somehow they represent the boundary in there too. Oh, this is a little subtlety I can't get into. So there's something. All right, now here's still another thing which had to be completely revised in thinking in order to get into the subject. So when I was being taught what a function was, for example, and a mapping and function were made basically the same thing with different words for the same thing. And but what it was always was something single valued. It had a domain, and you mentioned it was like you have to mention a domain, and then you mention the function, and it was a set of pairs, so it had to be single valued. So the concept of a mapping was from a set X, say, some set to a set Y, and it has to assign to each set an X exactly one Y in the set Y. And now why wasn't this good anymore? Why couldn't we just live with this? Well, look at the subgradient mapping. The subgradient mapping it's clearly important, and it assigns to a point in the domain of a function, in the effective domain, and may assign, no, let's go back here for a moment. So here at this point, it assigns, there's a whole range of vectors it assigns, and here even bigger range. But if, for example, I had here, instead of the curve coming down here, it came up steeply, infinitely steeply at the end, there would be a point in the domain where it's finite, and there would be no subgradient. So a subgradient can, I could have it be empty, or, well, I take it to be empty if X is where the function is infinite. So here we have a set valued mapping. What should we call it? What terminology? It's awkward. Economists deal with it, they call it a relation, but there's something too static about a relation. There's something about a function is dynamic. I love the fact about a function that there's an arrow. I don't want to just think of it as a bunch of a family of marriages of X's and V's or something like that. I want to think of it in this dynamic way. So, okay, so we have this, and then it's not just that we have a set valued mapping, but we have the challenge that sometimes the set valued mapping is single valued. How are we supposed to deal with it? The set valued mapping can be single valued. If people talk about a set valued mapping, then they want to think about a space of sets. So they have Y as a space of sets, and I have a space of points X, and then I have a space of sets, and assigns to each X a set. But that gets awkward. So the way we look at it instead is looking at the graph as a subset of a product space. And it could be any subset of the product space. Here I'm thinking of as kind of donut-like space. And at a given X here, there may, well, some X's there may be nothing, but if I take this X here, then I have all these points Y and the points Y corresponding to those. And then this would have what we call the effective domain. It would be this projection, the effective domain. And so any of these, we would say Y is an M of X. Well, we have a little trouble with notation because sometimes I want to say Y equals M of X because what if it's single valued? So this is something our notation is really difficult, but the concept is simple. It's just that the notation and terminology is somewhat troublesome. But anyway, nobody wants to talk about this. In those days, when we were starting out in this, nobody wanted to deal with that. And then they would use other words. Multifunction was a popular word in France, for example, for what this should be. How can we work with these? Well, we have to work with them. But they make some things simpler, because if you just have this generality, then it's easy to take the inverse. If you have a mapping that's just corresponding to the set, then to take the inverse, all we have to do is reflect it along this line. In other words, just reverse all the set of pairs, and then you get something else. All right, but then there are other things. Here, this is a set. It has geometry. If you have a set with geometry, maybe we can study this geometry. Maybe it has tangents and normals. And this would be some way to understand set valued mappings differently from what anybody did before. So this is very interesting, because if you can accept this idea of a set valued mapping that isn't just to a space of sets, then it leads to very much more things. All right, now how did this evolve in problems of optimization? So you all know about nonlinear programming. So nonlinear programming, although I'm somewhat irritated by this subject, because for ways I will explain maybe in a minute. So nonlinear programming, of course, grew out of linear programming. Had linear programming, you were going to minimize a linear function subject to linear constraints. And affine would be the better word, maybe, because at least here I'm taking all the right sides to be 0. So anyway, that would be, but then if it wasn't linear programming, it would be nonlinear programming. But here there was a kind of a big mistake made in setting up this as a basic model. I'll get to this in a moment. But this is then in this you would have constraints, which I have here as inequalities or equations, and they would define a certain set of points x, and these were the feasible solutions. That is, feasible, that is, you could consider them candidates. It's kind of a word for candidate solutions, but they satisfy the constraints, but they are not necessarily candidates for a minimum. But they're the ones that you can consider for the minimization. And by the way, I might as well give my complaint right away. The thing I complain about this model is it puts all the structure into the constraints and doesn't put any structure into the function f0, which is simply assumed to be a nice function. But it may not be a nice function. It may be a non-smooth function. It may be a composite function. So I think this was unfortunate that the model was set up this way too narrowly at the beginning. Maybe I'll be able to explain that a little later in better connections. So, but what I want to say about this now is that where this function was looked at in terms of a set C, a function on a set C, we can instead use this trick of extending with infinity. So now we can look at, you can just take you could extend it, but then why this? So you could take any function on the real lines that might have infinite values. And then you could consider the problem of minimizing it over the whole space. But then you could say, well, the points where the function is not infinity give you the feasible set, because when you minimize, nothing can be worse than plus infinity. So automatically you will take a point where the value is less than infinity. Unless there are no such values, then the problem is infeasible. And of course, in a nonlinear programming case, this is just that simple extension. But there's so many other ways now in which you could, so this breaks a kind of a stranglehold of a special structure in it. You don't need this. Now, I'm not saying structure isn't important. When we solve numerical problems, we have to use structure. We use more and more structure, but you don't have to have the structure up front. Like, you don't have to say everything about your personality when you're meeting a stranger. You can wait a little bit before you say everything about your personality. So an optimization can be a little more discrete for a while. We can deal with it on one level, and later we can look at all the good and bad parts of that particular function. And then in this framework, a local optimality we can try to see is something like a zero subgradient. Could we get that? But this means then we would need subgradients. So we have to like functions that are not necessarily, they might just be coming from nonlinear programming like this. I just take the objective function, I just use these, and then what would I mean by a subgradient? Somebody needs to make a good definition. The definition of convex analysis wouldn't work. You need some definition, and you need to show how to calculate. You could calculate with that definition. And then, of course, that's it. And then you'd want to be able to divide, to get necessary and sufficient conditions from that. You need a whole calculus that would cover this kind of idea. And that's obviously got to be a big job. And you would like it to cover classical kind of calculus too. Classical calculus should, to some extent, fit as a special case of the kind of calculus that you would have out of this. And notice again, just the very fact that we're using infinity here is something that people in traditional areas of mathematics really are not comfortable with and they don't like. And of course, I when I was beginning this, you remember, you know, and now I'm a very old person, but once I was a pretty young person. And so I was just in my 20s when I was working on these ideas and thinking how we should have functions with a value infinite. I wasn't the only one. Moreau liked infinity values for functions as well, but what's wrong with it? Well, then the negative, people want to be able to multiply everything by -1 without changing, but we have a one-sided subject. The subject has to be one-sided. There can't be any other way to think about it. So we have to think of plus infinity and minus infinity as different. We have to work in a way that accommodates it. But this again is something, it's a different form of analysis, which was hard for some people to accept. In my own career, as I was a young professor, I was first at the University of Texas, and then I spent a year at Princeton University, and that's when I gave a course on convex functions, and Albert Tucker asked me to write a book, Convex Analysis. In those days, people in optimization, like Tucker, this is the Tucker of Kuhn and Tucker, they know how important optimization is. But when I was then later at the University of Wisconsin, in Washington, University of Washington, I grew up in the state of Wisconsin, that's why I say that, but University of Washington, I had colleagues who appreciated the fact that I was working with convexity, but most of those people were interested in either convex sets in geometry, or they were interested in Banach spaces and the geometry of balls of Banach spaces and things like that. They weren't interested in optimization. And I had trouble getting promotion and raises in salary. People say, well, what you're doing is not very interesting. I had one person, kind of opponent, who was in harmonic analysis, and he said he once heard a lecture on linear programming, and it was just elementary algebra, he said. He had no idea what linear programming was, other than it was something algebraic. So that was his view of optimization. So there was a lot of headwind in all of this. Anyway, these are reasons of why it has been very interesting and exciting to have a new subject develop, and that's what I'm trying to tell you about in these lectures. I'm going to get into more details. Right now, there's this idea of variations. I was already talking about variations in the sense of convex, the calculus of variations. In the calculus of variations, we're looking at perturbations of parameters on which a problem depended, or things like how you could move a point within the constraints, in particular, varying a point within the constraints, and see how that might affect the concept of a minimum. But there's another idea of variations, because you can vary a problem for other purposes. Well, one idea is that you could approximate a problem. So variations of a problem you could also interpret as approximations of a given problem. Now, everybody knows how absolutely important it is in practical work to make approximations. We can almost never solve the real problem. But all in life is approximations. We deal with the top of a table. We think of it as a plane, even though it's not an infinite plane. And in reality, it's just a bunch of atoms with holes between them. So there's some approximate concept. And our models are, but even our best models of approximate models, they may not be so easy to solve directly, and we have to solve by approximations. We make quadratic approximations of non-quadratic functions. We approximate constraints. We have penalty functions. We have all kinds of ways, at least temporarily, to approximate a problem. Now, how would we want to look at it in this much bigger picture of variational analysis? Because now, this is actually, to me, a very thrilling idea. You want to think about a problem. Okay, now we all have seen extremely complicated problems. We know that in optimization, we're going to deal with problems that have millions of variables or millions of constraints. But for the sake of understanding a basic concept, we can think of this as we're just going to minimize a single function on Rn. Now, n could be equal to millions, but that doesn't matter for this. So at some space, it could even be infinite dimensional, of course, but I'm not talking about that. we have some, could be a big face, and we have a single function. And everything is just lumped together by how we define that function. For the moment, it's a single function and could have infinity. So how are we going to consider how to approximate, later we can get to more detail, but from this point of view, we have a function on our end which may have infinite values, and we want to approximate it. So we have to look at two such functions. F and G are two such functions. How can we say that they're close together? Now here you can see immediately the failure of classical ideas, because how would people look at this classically? They would look at the difference of the two functions. They would look at the absolute value of f of x minus g of x, the absolute distance at x. Then they would take like the maximum of that, some uniform norm, the maximum difference between f of x and g of x over some set of x's. And they would use that kind of concept to say that the functions f and g are close together. But that doesn't make sense if the functions could have infinity values. At best, that would make sense if the set of points where they are finite are identical. But that's not what we want in optimization, because in optimization, we can approximate constraints as well as objective functions. So if we're thinking of an approximated optimization problem, we have to imagine that the effective domains of these functions are being approximated are different also. So we cannot look at it. There's no classical idea about the difference of about the closeness of functions. There's no answer to this at all in classical theory. When are f and g enclosed for functions of this type? But if you look at the geometry of it, it becomes clear fairly easily, because you can look at, it depends on the epigraphs of these functions. So to make the picture clear, I'm very primitive, I'm afraid, at these graphics. So I'm drawing, this is very simple. I'm drawing these pictures in pencil, and then I am copying, but I don't have any color in it, so I can't use that. But anyway, you can see if you look at the right of this, you could say that the function f at this point you see there, that this function f jumps to infinity. So here this would mean that that's the constraint. This is the constraint set here. This constraint set is between there and there. The domain of there would just be that in this picture, just an interval. But the function g, maybe it's this corner here, but now it has this line up here. This looks like a linear penalty. You have something like a linear penalty. So here right away, you see that you want to approximate f by a function g, you have to allow for points where g is finite and f is infinite. You can't say that the value of, there's no way to say that the value of the f and this area is close to the value of g, because the value of f is infinite. And over here, we see something a little different again. We see that the effective domain of g, although it jumps to infinity here, so there's a constraint, but this effective domain is larger than the domain of f. So we have to think of functions in this sense, but you can see that this is captured very simply by saying, if I look at this epigraph of f, and in this case, the larger epigraph of g, the epigraph of g is near to the epigraph of f. And I could imagine that as this point moves over here, and as this line, and as if this point moves up and this line becomes more vertical, I could think of the set G as getting closer to the set F. So what we want is the closest of epigraphs. And that's the subject that leads to variational convergence, variational approximation, which is something I will be talking about in one of the later lectures. But again, you can see, well, this is, okay, when can you say two sets are close to each other? There is actually a theory of that. The problem with that theory, it's a wrong-headed theory. I like this example because it shows how you should never think I don't have the greatest respect for pure mathematics. I love it, but pure mathematics has to be inspired by things, and then it can carry on forever, but it has to open to inspiration. And sometimes people develop things without really knowing what they should do. And here's the problem. There's a big theory of set topology, spaces of sets. But how was this looked at? And still today, there are troubles over this because the standard theory in mathematics is very narrow. It's very general in some way. You look at sets in arbitrary topological spaces. Arbitrary topological, open and closed sets in arbitrary topological spaces, or maybe metric spaces. What's wrong with just sets in Rn? Well, they're not excluding it, but here's what they are excluding: unbounded sets. What the classical theory of set convergence does, although it treats all these very general topological spaces, it always assumes everything is compact spaces. Now, that's very interesting in its own right. It's important, but it leads to bad terminology in the general case. And here you can see it right now, because these epigraphs are not compact sets. A theory of set convergence is not going to work for approximating one epigraph by another. And then here's another problem, that in this classical theory where they say a set, in this case, you have to think of a neighborhood. Let's imagine in this classical theory what a neighborhood of this set would be, F. Okay, well, one idea is you would look at all the points that are of distance epsilon, that places of distance epsilon. So we put around this set F a kind of layer of fat that's epsilon thick around this set F. Okay, then they would say that the function F approaches G approaches F if it fits into such a epsilon layer of fat for smaller and smaller epsilon. But that absolutely doesn't work, because as this penalty, think of this a penalty expression, as this slanted line gets more and more vertical, it will never lie in this vertical epsilon layer of fat. So it's impossible, according to classical theory, for this function G to approximate the function F. So we would have to really, there are some more general ideas which had to be built on, but most of the theory was in this very narrow area, and it gave definitions which are wrong, like they call about upper continuity, outer, I don't know, upper limit of sets. They're all based on the wrong ideas of this classical theory, and that causes trouble. Anyway, so much about more complaints, but these complaints are connected with what was wrong, what was not working in classical theory, and what was needed for the sake of optimization. So it's why you need a new subject that brings in new ideas, but all these things are fit together. All these ideas have to go together. It's not just one thing. Let me just tell you another aspect of this, that when my book Variational Analysis was published, my former student Francis Clark reviewed it, and he thought that it should have just been about non-smooth analysis. It shouldn't have anything about set convergence in it. Well, that's wrong. All right, now we need to get on with this a little bit here. So this is the idea to approximate, but then you could think of a different idea here. So you could say that, okay, a problem is a single function on Rn, but now I could have a function of x on Rn that depends on a parameter b, a p. So I could have a function on this product space. And in that way, a single function on the product space could represent a full family of functions with parameter p. And then the idea is, then how does this problem depend on p? And then we get into this idea, is there some epigraphical, but you see here again how it all has to fit together. If I want to think of approximation this way, then I have to think of how p associates an epigraph as a function of x. So p goes from, this is a set valued mapping. Or I could look at the solutions to minimizing this problem. That would be a set of solutions. I have to assign to p a set of solutions. We'll be looking at all that later. And so you have to be able to deal with a set valued mapping. And it's with an unbounded set again. It can't just be bounded. We have to allow unboundedness. Right? And then this also gets into a different idea that we need Lipschitz continuity. Lipschitz continuity has to do with sort of uniform local bounds on differences between two things. And in classical mathematics, and take a sip of tea here. Lipschitz continuity is a consequence of continuous differentiability. But now we're going to be an area where we don't have continuous differentiability, but we might still have a finite function that could have this property of Lipschitz continuity, and that can help without differentiability, as I say. And the interesting thing here is that differentiability, when you think about it, is trying to quantify infinitesimal rates of change. We have this limit going to zero. What is the rate as the limit goes to zero? Infinitesimal rates of change. Whereas what Lipschitz continuity does is quantify the possible sizes of changes. The sizes can't be more than some kind of thing controlled by this kappa constant here, something like that. So both differentiability and Lipschitz continuity have to do with changes, but they're looking at it from a different way. And then there could be this solution mappings, and we might have some p-dependent problem. And then we get into something about error analysis. That's also going to be in one of the later talks. So if I have, I could say that I have a problem that depends on a parameter. Here's this p. And then for each of these parameters, I assign the set of solutions to that problem. The set of solutions to that problem. So it's a set-valued mapping. And then I can ask this kind of question that is fundamental to numerics. If there's a solution for this particular, this is supposed to be a p here, the typo. If there's a solution corresponding to this p, and this should also be a p. And then if I switch this p to, well, let's just call it, if I switch to a p that's near to this capital P, will there be an x that's near to it? And then how might this difference compare with the difference? So here we are. Maybe I could put a bound, kappa. This difference is less or equal to some kappa. That leads us to a concept of metric regularity, which is very close to Lipschitz continuity. Okay, now I'm just going to summarize a little bit, and then we'll get on to something that's a little more fun. Let me just tell you, give you a taste of it. So anyway, just to summarize, the distinguishing features of all this work to create a variational analysis, which many people have worked on. I may have been one of those pushing it the most, but so many people have worked on, and it has such historical roots. But one of the things then is it has to have one-sided variations because we have one-sided constraints. And then all we learned about convex analysis has to play into this. It has to build on that and those ideas. And then it has to have a calculus, subgradients, subderivatives, variational geometry, which will be in the next lecture. It's called a geometry calculus. And then it has to deal with extended real values, infinities, and set-valued mappings. All these are absolutely essential. And then, of course, it has to pay attention to its sponsor. It has to provide support from and inspiration from numerical methodology. That's one of the wonderful things about this kind of working in this subject compared to others, because we're always very close to computers being solving things because smart people create smart programs using smart ideas, and these ideas depend on things that can come out of variational analysis, optimality conditions, stability analysis, metric regularity, and so forth. And this also involves novel approaches to approximation, which can play into all kinds of numerical methods, as well as just mathematical modeling. So the books that are in the background of this are probably obvious to most of this audience. So there's also, first of all, there's the book Convex Analysis, and there's the Variational Analysis book I wrote with Roger Wetz, but then there's also the book with Sendonchev, which has got second editions. I never got a chance to have a second edition of any of the other books. And that deals with implicit functions and solution mappings, which I'm going to be talking about more at the end of this. And by the way, the sad news is my co-author, Sendonchev, died in September of this year. And that was a great loss. He was only 73 years old. And here I am, almost 87. And he's only 73. That's just terrible. A very, very close friend of mine, maybe my best friend of all time. And then in particular then, I want you to know that in these talks, I'm not going to give references who did what, when, and where to find, but these commentaries of these books are all pretty extensive. They explain a lot about the background, and you can get all kinds of stuff here from my website. All right, now I'm going to go on to something which is a little unauthorized. I know everybody's getting tired of mathematics, and I'm not going to show you mathematics. I'm going to just tell you a little bit about me. Because some of you may be wondering, how can it be that here's this person who's telling you about all the things he did in 1961 and 62, and here I am now, and I am very much alive, very much excited, very interested, very hardworking. Everything's going. So much fun. It's not all that usual, but I'm not the only one who can do this. And I'm going to give you a little background about my personality and what this fits. So first of all, not everybody here really knows much about the region where I'm coming from. So I like the satellite photo, and we have two people from this region. So we have Jane. So anyway, in this picture, this is on the left, you have the Pacific Ocean. And then you have this arbitrary line between the United States and Canada goes more or less right through here, east and west. Even though this is really geographically one region that never should have been divided up. But the border actually goes around kind of this way. And here is the city of Seattle. That's right. This is all, actually everything is urban, but the main city of Seattle is this. And this is the city of Vancouver. And this is Victoria. This is where Jane is, and Victoria, and we're all very near together. And if you can make out this little thing like a worm in here, this is a big island. It's one of the biggest islands in the United States. Of course, it has nothing to do with Vancouver Island, which is in Canada, which is a dinosaur compared to this tiny island here. But this is Whidbey Island. Okay, now Jane lives there. I have a house in Seattle right near this lake. This part is a lake, but I also have a house up on this island. This is Whidbey Island on a beach. And all around you see all these things. These are snow-capped mountains. So much adventure. There's more snow-capped mountains than the Olympic Peninsula. And then you have all these islands, all the sea. All the sea comes in and out of here. Anyway, and then so much of my inspiration that keeps me going in mathematics is also exploring wild nature, and I have a whole life of doing that. And I'll just show you a few pictures of this. Here's a picture in a forest where we have the ancient trees. We have forests where no one has ever come to cut down a tree. Where are these in the world? Not so many forests are left like this in the world. We have them in Canada, in this part of the world, in Canada and the United States. We have such beautiful forests and these trails. I love forests. But then also I like exploring lakes. Here's a mountain lake, and that's me in this picture. And this is an example of a lake that there's no road to this lake. In fact, there's no trail to this lake. And to get to this lake takes about 3 days. And you have to walk some parts of trails, and then you have to leave a trail, and you have to just go through rocks and cross through bushes and use maps and things to find how to go. And I just love exploring all these lakes. I spent decades, a lifetime of exploring, trying to reach all these lakes, different lakes. And then here's a picture of this is a picture just from a little while ago, October. In this picture, you see me in a kayak. And this is at the beach at my house on Whidbey Island. It's on a beach, and in the distance, you see my favorite mountain here. This is a glacier-covered volcano, Mount Baker. Jane is very familiar with this Baker. This too is a big landmark. In this picture, it's actually 100 kilometers away, and it looks so big. And here, right on the beach here, you see a bald eagle. This is the kind of eagle that's on the dollar bill and so forth. And I just did this. One of the things I love to do is in the evening go out in a kayak at sunset. And that's what's happening in this picture. Finally, the final picture is just this. This is another example of a mountain lake. This is a picture which is about 70 or 80 kilometers east of Seattle in the mountains. But again, to get to this point, to get to the point where you take this picture, you have to walk for about 3 days, mostly through wilderness, wild areas, some trails, but eventually the trail goes up. Eventually you have to leave the trail in the valley and just climb up through this. anyway, combining this always inspired me to get out in nature, always gave me better mathematical thinking. But also, of course, I'm a big music lover, classical music, there's literature, and there was all that travel. And I've so much enjoyed all the people I've met and collaborated with. And some of them are listening to this right now. And I just hope to see them again soon. That's the end of my talk for today. Thank you.
Thank you, Terry. It was a very inspiring talk, very interesting. Do anyone have questions? You can ask questions.
Maybe I ask more general questions so others can prepare for their question. So Terry, this is a wonderful introduction about the origin of this variational analysis. Now, here is the question about the future. What's next? We talk about the convex analysis, variational analysis, in particular about set value analysis. What's the next topic you want to focus on? Go beyond the variational analysis. Now, this for
I see. I see a lot of the work now is there's so many things in the area of probability and uncertainty that still need work. There's so much more about risk and about, there's I won't have much time to talk about it, but you have a problem. The problem is uncertain. Okay, the problem is represented by the epigraph. Okay, you could have a random problem. So then this must be a random epigraph. Okay, so you need a theory of random set valued mappings or random sets. Actually, Roger Wetz has developed quite a bit of this, but there's so much yet that needs to be applied. There are all kinds of things about, I don't know, generalizations of processes. There's all kinds of probabilistic, stochastic kinds of things which are not statistical things which are being looked at in much too narrow a way, I think. So that's certainly a region where, then there's just many kinds of applications. So many of you know that I myself am very interested right now in augmented Lagrangian methods. Well, I always have been, but coming back to it, and how to apply variational analysis to this, how to understand optimality. So this is not exactly a new subject beyond variational analysis, but it's the potential is there to do so more things that people simply don't know. Maybe I'll think of some more examples in the meantime, and then I'll tell you when we come to the other lectures. But I often run into this. Oh, if only I have some time, I would try to look at the subject through the lens of variational analysis and try to look at it in a different kind of a way. Because so the difficulty, as you well appreciate, is that people's education does not even include convexity, really, or not to mention, optimization, and they are educated in the classical analysis, and then they don't really know how to approach these subjects. So many very smart people in engineering get into optimization, and they just don't really know. Okay, here's a good example. We all know how important neural networks are. Neural networks. Now, if you look at the formulation of a neural network, I don't want to say it's not successful, but the whole formulation is kind of stupid. There's all these things, they're two-sided, and then they have so many parameters. Somebody should be able to do a much better model than a neural network. But you see, instead, people say, well, this is what a neural network is, and now what we're going to do is solve it better, or we'll do something numerical better with it. But what about having a different model? What always has interested me is not just the computation, but do you have a right model? Is this a good model for something? So I think there are many areas where these ideas, the very ideas I'm explaining, need to be worked out in a new context by people. The people who invented a neural network didn't even know anything about optimization, much less about variational analysis.
Okay, that's wonderful, Terry. I can ask many questions. I think I better leave this rare opportunity to other people, particularly to young people, to ask you questions. Ask you questions later, not today. I think I leave the opportunity to others. Thank you, Terry.
Maybe they are not ready yet. How about I ask a question? Terry, so thinking about the terminology, so what do you think about the non-smooth analysis? Is it the field within variation analysis, just deal with differentiability of functions?
Well, I see non-smooth analysis as basically something like analysis where you don't use continuous differentiability or even differentiability, some kind of analysis without differentiability. But it's an historic term. We can continue to use this term, but I think it's too limited, really, because for example, when people say non-smooth optimization, then they say, well, okay, I have something like nonlinear programming, but the objective function f0 isn't differentiable. It's true that there are many problems like that. I agree. But what I object to in that case is just taking the function f0 as not having any structure. Maybe it's composite, for example. So I think that many models in mathematics have easy and difficult parts. And what you want to do in setting up a model is somehow isolate them in a useful way. What in the model, where is the smoothness? Where is the differentiability? On the other hand, where is the other aspect? And you try to set it up in a way that you can deal with them directly. So I completely agree. And there are many functions we have, like value functions from something with a structure is not going to be a composite structure. And we do need to study things, but I'm not sure that non-smooth analysis covers so clearly infinities. It seems to me a little more, it's like a finite function that's just isn't differentiable, but maybe that's just my, what the other part of it is, as I say, is that non-smooth analysis is just, it's just the differentiable part of it. And I think all these other aspects like approximation and convergence are also really important. And I don't see that the term non-smooth analysis really covers that. So what I suggest is to look at the variation of the definition of variational analysis that I wrote at the beginning of the variational analysis book, where I tried to put together why we needed a more comprehensive term and why that might be a good one. But we can talk about non-smooth analysis. I agree.
Yeah. So it would be a subclass.
I think of it as a subset of it. Yeah. In particular, the omitting most of the conversion stuff and thinking more about the sub-differentiability type stuff.
Thank you.
Hi. Can I ask a question? Professor
Yes.
Rockafellar, hi, this is Donglei Du. So I'm kind of a lay person in this area, but I mainly have a discrete optimization background. I have a question. So about this variation analysis, can that handle like discrete problems, like where the domain is kind of a discrete?
That's right. That's right. That's right. This is intended to be a generalization of calculus with basically sort of continuous things. It's true. It's true. But it doesn't mean that the subjects won't come together, because for example, that in discrete optimization, you often use models with like Lagrangians for lower bounds and things like that. So there's it's going to be a combination of things. And furthermore, not all problems are totally discrete. A lot of problems, there's some mixture of continuous and discrete. And how would this be handled? So another idea is that sometimes the discreteness might be represented or modeled by something which is like a non-smooth function. But my own background is not although I've done some things with discreteness, my own background is the kind of thing that I've been talking about now, which is mostly about continuous or, continuous mathematics. Of course, I don't mean continuous functions. It could be lower semi-continuous. There are many problems, but they're not really designed for purely discrete problems.
Thank you.
Any other questions? Terry, I have another question. So if so it seems we have, yeah, we have a lot of applications in optimization. I'm wondering if there are applications in other field. I mean, potential more applications in other field.
Variational analysis?
Yeah.
Yes. Well, for
Seems
example,
other,
I think statistics would be a very good example. Statistics.
Yeah.
There must be many applications. There are already some applications, risk and
Yeah.
statistics, but there are, many of these things are not yet really explored because the people in
Yeah.
these subjects don't know enough about how to use them.
Yeah.
But let's put it this way. A lot of subjects have variational principles or some kind, like statistics has optimization that comes in a sense of likelihood and things like that. You know, there are lots of, there's maximum likelihood. There are various optimality things concerned in there, but also in a lot of that theory, a lot of it is like in a classical frame that everything is two-sided. There's somehow the one-sidedness doesn't come to this. And I know, for example, I worked at one point, but there must be so much more in this area with one of my students, Alan King. So you had the solutions to some optimization for a stochastic programming problem, and there's something random. So he ended up with this random solution, but then there's something about a law of large numbers that you try to create out of that, but it's not going to be approximated. You're not going to get classical Gaussian types of approximation. It'll be sectors, different kinds of Gaussian sectors. There's this one-sidedness is somehow not exploited or embraced yet in so many of these areas. Again, maybe as we go along, I'll remember some more of these areas because I've dealt with some in the past. Of course, economics is a big area. One of the areas I'm also particularly interested in is the theory of economic equilibrium. And there's certainly a variational analysis that becomes in and quite importantly.
Yeah, this development from equality to inequality, one side, both sides to one side, is very fundamental because in early times, Lagrange multiplier can only apply to the equality constraint, right?
Yes.
Not until maybe, when was that? Not very long ago, right?
No, actually, in the calculus of variations, they played with all of this stuff but there was historically, it's interesting again because so much has to do with communication in mathematics. This isn't just people writing papers. So the people working on the calculus of variations in the University of Chicago in the United States was, for example, one of the big schools of this subject, and also some people in England, and they worked on problems of curves with equality constraints on endpoints and things like that. I don't remember they worked on them with inequalities, probably just as a pure mathematical exercise. But then when the Russian schools started doing control theory, they reinvented a lot of the same kind of the theory because, but inequalities for that kind of a subject. So, and they did have Lagrange multipliers, Jane, for those things back then. In fact, there's Karush, Kuhn Tucker. Karush was a student of who was it? I can't think of the name right now, but McLean, McLean, I guess, an important person in the calculus of variations. And you know how it is, professor. I hope there aren't any students listening to the secret of a professor, but you give a problem to a student, and you don't want the problem to be too hard. So you give the problem to a student that you already know the answer to, but you don't tell the student that you already know the answer. And then the student does this answer. And it's supposed to be a problem that's interesting, but it's not terribly important, or you would do it yourself. All right, so I think it happened with Karush that the calculus of variations, okay, you can have these Lagrange multipliers for inequality constraints, but it's just like a graduate student exercise as far as somebody in the calculus. The professor thought that this is a good thing for a student to do to get a master's degree, you see.
Oh.
We understand that this is one of the most important contributions to the subject, the contribution, but it's because it's an example of this subject being developed without connection with an application as we know it.
So Caruso's thesis
This would go
in
back to the
19,
30s, I think it was. I can't remember the 30s.
yeah, 1939, right? His thesis in
Yeah.
1939 was not known until.
It wasn't Kuroshia. It wasn't McLean. It was I should know the name of this. Anyway, somebody that Hassan Doncha was very fond of, who invented things like metric regularity stuff in a certain sense. But anyway, that's right. He discovered that this Caruso was a student of that person. I can't think of the name. Sorry. Names escape me sometimes. But anyway, it's a student story.
Okay, I see. Okay, so Caruso's supervisor was studying calculus of variations.
Yes, it was in calculus of variation, all of that, and it was part of that whole school. They were all at the University of Chicago, so they were having seminars and all of that. They were doing things like that. But I don't want to answer that phone call. Wish I could. It'll stop. And so ideas are in the air, and so those things happen. But only later was all this rediscovered and put out. And when I was learning all of this, it was only Kuhn and Tucker. But of course, Kuhn and Tucker were also, in a sense, not independent. Gale, we have all these. The theory of linear programming is in many ways due to John von Neumann, not to the others. He was kind of suggested to them, and then they sort of, as graduate students or professors, out these ideas, but those ideas mostly came from Neumann.
Oh, really? Interesting.
Yeah, right. He invented game theory. He knew all about duality, saddle points. This is all from Neumann. And then he saw this thing in linear programming and he said, well, this is what ought to happen. Oh, yeah, they worked it out. It was sort of like a master's thesis.
Yeah.
Well, some people must be waiting for breakfast in China, and I'm waiting for dinner in Seattle.
Yes.
Actually, Terry, in China, they work very early. They start to work
Oh.
at 8 o'clock, even earlier than that.
And they eat breakfast before they work, even too.
That's right. So
Yeah.
that maybe
Yeah.
this.
Right. Is that right? Okay, then they're waiting for lunchtime.
Yeah, almost the 11 or after 11, they will go to lunch. They work very hard. It's different. Yeah, I came to my office at 8 o'clock in the morning, so this is 5 hours already working and listening to your talk. Yeah.
Okay, I'm glad we have this one time window. I thought there might be other people, colleagues who might watch it in Europe or some kind of place but I realized that the only good places to watch are in the Pacific Ocean or Australia, between us, between your time zone and mine. The only other daylight times during this lecture are mainly in the Pacific Ocean or Australia.
Mm.
So people in Europe would be in the middle of the night for them, for example. So,
Yeah, that's all for China and the US, right? In the morning time,
that's right. That's right.
Time.
But at least we found one feasible solution. There was one feasible solution.
So we are used to that now. We are actually running lots of talks and events, either in the morning or in the evening.
What was the question? When do
I don't have questions. So now we have many activities between the US and China, right?
Oh, yeah,
so we can arrange all either in the morning or in the evening.
That's right. If it's joint, now that we're stuck with this, but we could go back to flying.
Yeah, when next year? Can you predict that?
I don't know. I'm not sure I'm ready to do it myself yet because
actually I reserve something, let's say next December, to see if it works or not, right?
Okay. In Hong Kong.
All the people here miss you because you came here almost every December in the past, let's say 10 years.
I missed it so much. Yep. And
we are used to that. Yeah.
Yep. I went up to the top of Victoria Peak to see the blooming camellias. I love it.
Yeah.
Yeah,
And
the three
rhododendrons,
dimensional
why
shape.
rhododendrons?
Yeah, wild rhododendrons too, yeah, right, yeah. Yeah.
So there are no questions from any other
Yeah, no
students
questions,
or young
then
people?
we,
Yeah,
yeah,
that's it today.
Okay,
Yeah.
tomorrow.
I
okay,
think we'll stop.
okay,
Yeah.
thank you, Terry.
All
Yeah,
Thank you,
right,
Terry.
thank
Thank
you,
you, Jane.
I very
Yes.
much
Lovely
enjoyed
hearing
it,
about
and
again.
thank
see you
you,
tomorrow.
yeah, I will see you tomorrow.
All
Yeah, see you
right,
then. Okay,
okay.
bye-bye.
Yeah, bye.